Welcome to all. In this lecture, we are going to discuss about domain theory of ferromagnetism or Weiss theory of ferromagnetism. We know that there are three types of magnetic material: dia, para, ferro. In that, third one is ferromagnetic material. You know what is ferromagnetic material? So it is the material even without any applied field, it has some magnetic property or it has spontaneous magnetic moment. When the electric field is applied to ferromagnetic material, the material is strongly magnetized in the field direction. This process is called magnetization. That is, when the magnetic field is applied to ferromagnetic material, material is magnetized. That is, each individual atomic dipole moment will align in the field direction. So this process is called magnetization. So in this theory, we are explaining about magnetization process. Okay. So first, we should discuss what is domain. Domain is the small region of ferromagnetic material in which atomic dipole moment of individual atom aligned in particular direction. So the resultant magnetic moment will be the only in one direction. Okay. So in this figure, we can see what is domain. It is the small region of ferromagnetic material in which dipole moment of individual atom aligned in a particular direction. Okay, so in this domain, dipole moment of all individual domains are aligned in a particular direction. So the resultant magnetic moment will be only in one direction, in this direction. Okay, so this is called domain. So it is iron is the one of the ferromagnetic material. So its outer view is seen in the figure. Okay. So this is the ferromagnetic material without any applied magnetic field. So the material or the dipole moment alignment is like this. This is one domain. Here all dipole moment aligned in this particular direction. This is another domain. Here inside the domain, all the individual atomic dipole moments aligned in a particular direction or same direction. Okay. So this the walls separating the domains is called domain wall. The wall separating the domain is called domain wall. Another name for domain wall is Bloch wall. Okay. Here the magnetic field is applied from bottom to top in this direction. Okay. So now dipole moment of all the atoms or all the domains are aligned in the field direction. Okay. When you apply magnetic field to ferromagnetic material, dipole moment of all the domains will align in the field direction. As a result, the material is magnetized, strongly magnetized. So this process is called magnetization. Okay, the process of domain magnetization. Okay, so we know that an unmagnetized specimen domains are randomly oriented and the net magnetization is zero, which was shown in the previous figure. Okay, when the external magnetic field is applied, all the domains will align in the field direction. As a result, there is a large net magnetization. Okay, so this magnetization process involves two steps. We are going to discuss about these two steps. Okay, that is, when the external magnetic field is applied to ferromagnetic material, the material is strongly magnetized in the field direction. The process is called magnetization. So this magnetization process involves in two steps. It includes two steps. So we are going to discuss about these two steps. The two steps is, one is movement of domain wall, second one is rotation of domain wall. magnetization occurs in these two steps. Okay, first one, movement of domain walls. What is movement of domain wall? When the small magnetic field is applied to ferromagnetic material, the domains with magnetization direction parallel or nearly parallel to field direction will align in the magnetic field direction. So as a result, these domains will start to grow, remaining domains will start to shrink. So this process is called motion of domain walls. That is, when the small magnetic field is applied to ferromagnetic material, the domain having the magnetization, its direction is parallel or nearly parallel to field direction. Those domain will start to grow, remaining domain will start to shrink. Okay, so this growth and shrink happens through movement of domain walls. This one is first step. Second step is, so when the magnetic field is increased to large value, further domain growth is not possible. Okay, when you apply high magnetic field to ferromagnetic material, further domain growth is not possible. At the time, the entire domain will orient or will rotate in the field direction. So that is called rotation of domains. When when the applied magnetic field is very large, so there is no further growth process possible. At the time, the entire domain will rotate in the field direction. So this process is called rotation of domain. Okay, now the material is magnetized. Okay, so in this two-step magnetization process, there is a certain certain energy also involved. So we are going to discuss about those energies. That is, 4 energies are involved. We are going to discuss about those 4 energies. This is movement and rotation of domain walls. This figure shows when the magnetic field is keep on increasing, initially domain growth and shrinkage is possible through domain wall movement. When the field is very high, so entire domain is rotated or aligned in the field direction. Okay, so next one, the energies involved in the magnetization process are magnetostatic energy, exchange energy, crystal anisotropic energy, magnetostrictive energy. Now we are going to discuss about these energies one by one. First one, we are going to discuss about exchange energy. It is the energy associated with quantum mechanical coupling that aligns the individual atomic dipoles within a single domain. Okay, so it is due to interaction of electron spin. Okay, in this figure, you can understand clearly. That is, it is the quantum mechanical coupling energy. Okay, it is the quantum mechanical coupling energy associated with the electron. Okay, inside a individual domain, all the dipoles aligned in the same direction, which is due to exchange energy or quantum mechanical coupling energy associated with the electrons. Okay. Second one, crystal anisotropic energy. It is the energy of magnetization, which is the function of crystal orientation. Energy required to do magnetization is the function of crystal orientation. Depends upon the orientation of crystal. So energy required for magnetization varies. Means consider a crystal. One crystal having 100 alignment, another crystal having 110 alignment, third crystal having 111 alignment. So the energy required to magnetize 100 crystal is very less compared to 110 and 111. So energy required to magnetize 111 crystal is very higher compared to these two. Okay, so it is the energy of magnetization, which is the function of crystal orientation. This is crystal anisotropic energy. This figure clearly shows the various crystal orientation of ion structure. Next one, magnetostrictive energy. When the material is magnetized, it is found that it suffers a change in dimension. That is, when you keep the ferromantic material in alternating magnetic field. When you keep ferromantic material in alternating magnetic field, there is a change in length takes place. Okay, so this effect is called magnetostrictive effect. Energy associated with this effect is called magnetostrictive energy. Okay, that is elastic restoring force. Elastic restoring force in the material is called magnetostrictive energy. Okay, what is magnetostrictive energy? When the ferromantic material is placed in an alternating magnetic field, the material starts to vibrate, or in other words, there is a change in length takes place. This effect is called magnetostrictive effect. Energy associated with this effect is called magnetostrictive effect. So the last one, magnetostatic energy. It is the potential energy associated with the ferromantic material. Okay. Inside the material there is some potential energy. That energy is called magnetostatic energy. If you divide the magnet into two pieces, potential energy or magnetostatic energy also divided into two. If you divide the material into n pieces, energy also divided. Okay, so each individual piece will act as magnet. This is magnetostatic energy. So now we discussed about all the 4 types of energy involved in magnetization process. Okay, next topic is pH curve. This is pH curve or hysteresis. So what is hysteresis? That is, this is the graph which is plotted between applied magnetic field and the magnetic induction or magnetization induced in the material. Okay, see this graph. Here, see, when the magnetic field is increased, magnetization also increases. When it is decreased, and when H is 0, so this magnetic induction also decreases, but there will be no 0 in the magnetic induction. Similarly, see, in all the places, this loop, this hysteresis loop clearly shows that there is always some lag of magnetization or some lag of magnetic induction in the ferromagnetic material behind the applied magnetic field. So this process is called hysteresis. What is hysteresis? Lag of magnetization behind the applied magnetic field is called hysteresis. Here we need to discuss about the two terms. One is retentivity, another one is coercivity. What is retentivity? That is the residual magnetization in the material. Here we are reducing the magnetic field and where H becomes 0, but there is some magnetic moment or there is some magnetization remaining in the ferromagnetic material. Here B must not be 0. Okay, when H is 0, B must not be 0. So this remaining magnetization is called retentivity. What is retentivity? When the applied magnetic field is 0, there is some magnetization remaining in the material. That magnetization is called retentivity. Next one, we should know what is coercivity. So to reduce this retentivity from this value, some value, okay, this value to 0, we need to apply magnetic field in the reverse direction. So this reverse direction magnetic field, okay, this HC is called coercivity. What is coercivity? That is to reduce the retentivity from M0 or B0. You can write this is M0 or B0. To reduce the retentivity from MR or M0, MR to 0, we need to apply some reverse magnetic field. That reverse magnetic field is called coercivity. So we discussed these things in this slides. Okay, what is the hysteresis? We discussed here what is retentivity and what is coercivity. So this is the hysteresis behavior of ferromagnetic material.